Hello, welcome back to your Module 5. So we are still on the influence lines on statically determined structures. And now we are on Unit 2, which is the influence lines for trusses. Where in your Unit 1, we discussed about the influence lines for beams and frames. Okay, so for this unit, our unit learning outcome is of course to draw the influence line for trusses. But before that, we need first to understand the load transfer mechanism of trusses, okay? Since this is where the difference of beams and frames happen together with these trusses. Okay, so the difference of trusses with the rigid connected structures, which are the frames and beams. So in this load transfer mechanism of trusses, okay, so if you say trusses, that could be a bridge truss or it could be a roof truss, okay? So the concept of the load transfer mechanism is the same. So for example, let's consider here, okay, this bridge truss, okay. So if you say bridge truss, we have here what we call as the deck, wherein of course that is where the traffic will flow. That is where the traffic will pass, okay. And then if you say deck, that is of course the slab, okay, that is the slab where the traffic will flow. But that slab will be directly resting into these members, which we call as the stringers. Okay, these are your stringers. These are the first hand members carrying the loads from the deck or from the slab. And then after that, that stringers is now resting also on another member, which is what we call as the floor beams. These are this cross section or this transverse member. Okay, so again, the slab is resting on the stringers, and the stringers are being supported by the floor beams. And then lastly, the floor beams are being connected, okay, the ends of those floor beams are connected within the joints of the trusses, okay. So if you will try to recall the assumption of trusses before, wherein the members of trusses will only be undergoing pure tension or pure compression, or we call that one as pure axial stresses. Since our assumption there on trusses will be loads applied, all the loads will be applied on the joints. Okay, so that is our assumption on trusses. So if that is the case, then the actual load is actually different. Okay, since the actual load could be a uniform or a distributed load, or it could be a concentrated load, but it might act on the members itself, not on the joints. So how is that possible, since our assumption in trusses that all the loads are applying on the joints is due to this floor system, okay? This floor system arranged in a manner that the loads will be transferred to the truss at the joints, okay? So this is the actual load of the truss. Let's say that is a distributed load, and then that will be converted, or that will be applied on the equivalent truss as a joint load due to this floor system. Okay, so again, as you can see, the last member that will be holding the load before that will be transferred to the truss are these floor beams, and all of this will be connected to the joints of the trusses. Therefore, the loads carried from the traffic will be transferred to the joints of the trusses. So again, our assumption still stands that all the loads on trusses will be applied on the loads. Okay. So again, so that concept or that load transfer mechanism is actually true also to the rough trusses. So in the case of rough trusses, live loads are transmitted in the same manner. So again, we can actually say that your load is the actual load is found on in any position here within the bridge. It could be within the member itself, or it could be exactly at the joints. But since due to this floor system, that will be transmitted to the truss as joint loads. Okay, so that is the transfer of load mechanism. Therefore, now let's try to have an example. So it says there that given this Pratt bridge truss below, the loads due to the traffic are transferred by a floor system at the bottom chord. So if you say trusses, we have actually the parts. We have the bottom chord, we have the top chord, and then this connecting the top chord and the bottom chord are what we call as the web members. Okay, that is of course the same, and it depends on the type of trusses, because of course we have the regular standard types of trusses like front truss and so on and so forth. Okay, so there are types of trusses wherein that is a commonly used type of truss on the roof, and there are types of trusses which are commonly used also on bridges. Okay, so one is this front truss that is commonly used on bridges, wherein your diagonals are parallel. Okay, so we are going to, since the loads are applying on the bottom part, okay, the joints of the bottom part, then what we are going to do is to draw the influence line of the members CI, CD, and DI. So what does that mean? We are going actually to draw the response. If we say response of the member, that is actually the reaction of the member. So if we are talking about the reaction of the member, that is the internal force. Okay, so the internal force of member CI, member CD, and member DI. So we are going to construct three different influence lines due to the response of these three different members. Okay, so if we will try to look at the figure, this is your CI. Okay, this is a vertical member CI, and we have your CD, a horizontal member, and the diagonal bracing, which is your DI. Okay, so that is suggested by the problem for us to construct the influence line. So, just like what we are doing on analysis of trusses, of course, since this is the same as analysis of trusses, only that our load is not permanent. It is now variable. It is now moving. So, we will first, before we will analyze the internal reaction or the internal force member, we need first to, of course, calculate the external forces, which are the reactions. And since, again, your loads are moving, so we will end up with a function. Okay? Your reaction will not be constant, rather that is a function of a distance. Okay? Function of a distance, x. So, the same thing, just like in beams and frames, all we need to do is assume unit load. Okay, it could be a 1 kip, since this, as you can see, these are distance, the distances are feet, so we can assume that the force could be in English. But if that is meter, you can assume there Newton or kilonewton. But actually, you can just say 1 unit load to make it general for English or metric unit. Okay, so just like before, again, you can assume at any location there and then indicate the distance as x, since again that is moving. But this time, our application of load will now be moving from joint to joint, since of course this is trusses. That is the assumption of the load application. However, the actual load is actually moving within the span. Okay, but since again due to the floor system, that will now be acting as transferred load from joint to joint. Okay, so let's say the unit load is this one, and then we will have a distance x, since again that is moving. Then we need to calculate the reaction as a function of distance x, okay, of our 1 unit load. So if I will to take a moment at E, okay, take a moment at E, let's say clockwise is positive, then I will end up with the function of AB in terms of x. Okay, so AB, that is a clockwise, and then the moment arm is, okay, by the way, the distances are equal, so this is 6 at 15. It means that there are 6 panels or span at 15 feet each, so total of 90. And then the height of this is uniform, that is 20 feet. So if you were to take a moment at E, and then that is at A, there are 4 panels, and that is 15, so 4 times 15 is 60. So the moment arm of our AB is 60, so that will be 60 AB, positive, since that is our assumption of clockwise, positive. And then what else are this, is this 1 unit load? Okay, it will create a counterclockwise, and then the moment arm, since that is moving, and we know that x is from A, and of course we know that A to E is 60, so we can actually write the distance as 60 minus x, that is the moment arm of your 1 kip, or the 1 unit load, which is a negative, since of course that is opposite the positive assumption. And then simple algebra, your AB will end up as 1 minus x over 60. So again, in case we want to calculate the response or the reaction AB at a certain distance of x, again, all you need to do is substitute the distance x. And then if you want to take now your, if you want to calculate the function of EB, or the response reaction EB as a function of x, you can take a moment at A, just like this. Or of course, since you already know one of that, you can do summation of forces vertical. Okay, so now we have your AB and EB. So we can now start cutting if you want to use the method of sections, or if you want to use the method of joins. But since in our problem we are after directly to CI, CD, and DI, we are not after in all the response of the member. So I'd rather suggest use the method of sections, especially if your member is within the middle. Okay, we need, since if you are going to calculate that one by method of joins, you need to start with the known forces, with the joint with known forces. So for us to get rid of that long solution, we can, it's better if we will use the method of sections. So if I want to start with CI, okay, so that is the CI, I can actually cut this way, okay, a diagonal cut section here passing through this panel HI and CD. And then if you want to calculate CD, I can use still that section, or you can cut the section IJ and CD, and then at the same time that will be exposing your diagonal member DI. So that is what we will be using. So first, let me assume a section. Let's consider that as section A, okay, for member CI, for the response of member CI. Since we need first, okay, so if you will try to recall the steps, first is you need to establish, okay, of course, indicate or put a unit load that is moving at a distance x, and then second is of course establish the equation, okay, of the response, and then using that equation we are going to plot the line graph of that, which is the influence line. Okay, so first is we need to establish the equations, okay, or the functions. So considering your member CI, okay, I want to cut this section AA. I will expose 3 force members, but first of course we will expose that one, so it depends actually if that is a tension or compression, but I'd rather suggest always assume the initially the tension side, but still you can use the, or you can assume a compression, but it's up to you, because if you will assume initially a tension, then in your influence line the positive there will be tension, okay, then it means the negative influence line on the response will be the compression. But if in your case you assume initially compression, then the positive on the influence line will be compression and the negative will be the tension. So for me, I will be assuming all the initial direction to be tension. So in our influence line later on, all the positive are tension. Okay, so I'll be exposing HI and then CI and then CD. But in here, our after first is for CI, for us to calculate the response of CI. So there are actually 3 possible cases here. Okay, when the load is within the section that we can consider. Okay, within this section that I considered the left side, so that will be a lesser figure for me to draw. But actually you can consider the right side. It depends, it's up to you. Okay, or you can use the both sides at the same time. You need to know but you need to consider the reversal. Okay, and then second possibility is that if your load is already on the other side, so this is now the second half. And then there is a third one wherein at the panel where the section is passing through. Okay, so we need to consider when the load is within the panel that we cut. So that is in our case CD or HI, but since our load is within the bottom part, then that is for CD. But if your load is of course on top, then that is HI. Okay, so first is if our load is within the section. Okay, so it means that is considering before C. Okay, before joint C, the load is here. Second is when the load is within the cut section, or that is the cut panel CD, member CD. And then third is once that will be after your joint D going through the end of your bridge. Okay, so I draw different figures for those. Okay, so first, second, and then third. So now for our first one, okay, first condition or first possibility, the load is within the section. Then let's say that is again where the load is at the distance x. Then since we are after the response of CI, I do not need actually the HI and CD. But if you want to calculate, then there's no problem. Okay, so for me, you need to choose between the 3 equations of equilibrium, which one will give you directly what you need. For in our case, we need only CI. So if I will to use summation of forces vertical, then I will get rid of the horizontal HI and CD. Okay, so CI, summation vertical, going up positive, AB and CI are positive, and then the only negative is your 1 going down, so that is a negative. Okay, negative 1. And then this will go on the other side, simple algebra, so this will go negative and this will go positive. And then of course substitute AB, and we calculated that one a while ago as 1 minus x over 60. Okay, simple algebra, that will be x over 60. So this response of CI, response equation of CI, is good only when x is from 0 to 30, since that is of course when the load is exactly at A, and then when the load is exactly at C. And then now, considering that your load is within your cut section, that is now your within the member CD, so when the load is moving within that distance, then we will be having this as another possibility. However, this time, we need to consider the effect of the 1 kip, since the 1 kip is actually within the member. Okay, the 1 kip is within the member. So if we will try to calculate the effect of that on the section that we are considering, then I need to calculate the reaction, since of course this is pin connected. These are pin connected members. So I will to take a moment at any joints of this, then I will expose the reaction. Okay. So if I have to take a moment at D, let's try to calculate, let's say that is the FC, or that is the imaginary reaction at joint C. So calculate FC from member CD by taking a moment at D. Let's say clockwise positive, so FC, 15, of course that is the distance or the length of one panel. So 15 FC, and then your 1 kip. How did I get that distance? Okay, we know that the distance X is from A. And then of course that is within your member CD. So 1, 2, 3, that is a total of 45, and then subtract the X distance from A, that is the moment arm. Okay, moment arm of this, since again that is already within your CD. So that is X, and we know that 1, 2, 3 are 15 each, so that's a total of 45. So the moment arm at D will be 45 minus X. Okay, 45 minus X. So taking a moment of 1 will be in negative, since that is opposite my assumption, this one. So simple algebra, you will have your FC to be 3 minus X over 15. Then that is what we will be carrying, since again, why will I not consider your 1 kip, since that is already out from the view of our section, or out from the coverage of the section that we are considering. Okay, so we need to integrate the effect of that. So we should not forget the effect of 1 kips, unless that will now be going on the other side, since of course that will now be our third case. If it already surpassed the cross section, I mean the cut section, that is already on the other side of the section, then that will now be actually neglected, since the effect will be applied on the reactions. Okay, so again that is FC, we need to calculate that again, since again that is not part of the section. So FC will now be included if I will to take summation of forces vertical. So instead of the 1 kip, that can already be forgotten. Instead, we will now focus on FC. So going up is CI, and then AB, and then going down is FC. So simple algebra, CI will be going as FC minus AB, substitute the FC, and then substitute the AB. Okay, substitute the AB. Simple algebra, that will give us 2 minus X over 20. And this equation, response equation of CI, will be good for distance of X 30 to 45. That is again within DCD. And then now the rest will be the third possibility, that your load is already on the other side completely. A while ago, it is not part of our section considered, but that is within the panel where the section is passing. So we need to carry the effect of that. But if that's already on the other side, that is actually already applied on the reactions. Okay, that will now be carried or reflecting on the values of the reaction. So that's it. If we are going now to consider your load after joint D, that's already in the other side. So our distance there is 45 to 90, the rest. Okay, so the same thing, summation vertical, but still we are focusing on the side that I am considering. Okay, so going up is positive, that's only AB, and that's it. CI is also going up, and there is no other force to consider, so that's it. Your CI will go negative AB, but your AB is of course the value 1 minus X over 60. So simple algebra, this will just become positive, and that will become negative, and then that equation or response is good for 45 to 90 value, the distance x. Okay, so now we are now ready to draw, given the response equations from 0 to 30, 30 to 45, and then 45 to 90. Okay, all you need to do is substitute and then plot, of course, your values on the graph. So when x is 0, that will be 0. When x is 30, that will be 1/2 or 0.5. So that is the first possibility when the load is within A to C. And then second is that when your load is within the cut section CD, so at x of 30, that will be 3/2. So 2 minus 3/2 will be giving us 0.5 or 1/2 still. So that should be connecting, since of course that should be continuous. And then of course when that is 45, that will now be giving us a negative 1.5. And moving on to the third response, substitute 45, that will be giving us still again a negative 0.25 to make it again continuous. And then lastly 90, that will give us a positive 0.5 or 1/2. So this is the response equation again for member CI. So again, if you need the actual member force in your CI, member CI, then you all you need to do is locate where the load is applying or where the load is located, read the ordinate of your influence line, and then multiply the value of the actual load. Okay, so that is for member CI, and the same step follows to your next member CD and DI. So when we cut the section AA, we actually expose also the CD, the member CD. So maybe I can still use that section, but this time, okay, for me to cancel out the HI and CI, I will take a moment at I. Okay, I can do that even if that is not part of our section under consideration. That is still an imaginary point, or that's actually an original point that we can use as a reference to cancel out the effect of HI and CI for me to get only CD. So again, before C, it means that the load is within A to C. So that is at x 0 to 30. I will to take a moment at I. Okay, let's say counterclockwise positive. Then we will have 20 times CD. Okay, CD. Moment arm is the vertical, which is 20 feet. That is positive since my assumption is counterclockwise. And then your 1 kip. Okay, your 1 kip is also a counterclockwise, so positive. However, the distance will be, okay, we know that the distance, the perpendicular distance, okay, at I is the horizontal distance. So from A to C, we know that that is 30. And then since the load is moving at a distance x from A, the moment arm will be the rest, 30 minus x. Okay. And then we will have the AB. That is now the opposite. It will be going clockwise, so it is a negative. And then the moment arm is 30, negative 30 AB. And simple algebra, this will be transferred on the other side. It will change sign and divide both sides by 20. You will have your CD, substitute AB, and then simplify, you will have x over 40. That is good for x from 0 to 30. Okay? And then again, we will consider that the load is within the cut section CD. So again, we need to calculate the imaginary reaction of those. Again, we do not need to calculate FD unless you are considering the other side, since that is what you will be considering if you are using the other side of the section. But for me, we are using the left side, so I will use the FC. Okay, so the same thing. So we calculated actually, since nothing changes. We only took a moment at a different point, but the load application is the same. Okay, and the orientations are the same. So what we calculated a while ago is the same. How we calculated that, how we get the distance is the same. So all we need to do is to take a moment again at I, but actually that cancel out also the effect of FC. So it means that actually we do not need to do that. By merely looking at that, you do not actually need to calculate FC, since that will be later on cancelled out if we will to take a moment at I. So that will only give us a moment of AB only. Okay, so that will be, let's say, counterclockwise positive. So you will have here your CD as positive, again the same, moment arm is 20. And then AB will be a negative 30 times AB. It will go positive, divide by 20, substitute AB, and then that will be 3/2 minus x over 40. Good when your load is within your span CD. And then lastly, the third scenario is that if that's already on the other side completely, after D, that is 45 to 90 feet. So now, the same, I will to take a moment at I. Now, what we can only consider there is the same still as AB and CD. Okay, only AB and CD. So actually, if you try to look at that, the same as this. The response when the load is within CD and the response when the load is within the other side is still the same. It means that it's a straight line. Okay, but we need to, of course, evaluate that one by calculating the response for us to see that. Unlike on the first one, okay, wherein if you try to look at this, the response when the load is within CD is different. Okay, when that is already on the other side. So now, if you try to plot using this 3 response equation, but this is already, as you can see, single equation. So when that is 0, that will be of course 0. When that is 30, that will be 3/4. 30 over 40 will be 3/4 or 0.75 positive. And then using now the second equation, if that is 30, that will still be 75, so it will connect. But if that is 45, we are talking about joint T, that will be 0.375. And then actually you can stick to this or you can proceed since that is the same. So substituting 45 will be the same, and then 90 will give us a negative 0.75. So that is the response. So this explains the same equation. It should be a single line or a straight line, since of course we are referring to the same response equation. Okay, and then finally we can go to the third member DI. Okay, so now since in my section a while ago, when I cut from the HI and CD section, I did not expose there the DI, so I need to change another section. So this could be your section B. Okay, section B. So if I will cut that, I will be exposing CD, ID, or that is the DI, and then IJ. And then of course, later on, our after here is the inclined member. So later on, if we will try to take a moment or summation of forces, horizontal, vertical, we need to know the breakdown of this, the components horizontal and vertical. So we need to know the slope. Since actually these are parallel, so the slope of this is the same as that. So if we will calculate the slope of that, since the span is 15 and the height is 20, you can reduce that one, divide it by 5. So 15 divided by 5 will be 3, and then the 20 divided by 5 will be 4. And then by Pythagorean theorem, the hypotenuse of that will be 5. Okay, 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, and that will be square root, which will give us 5. So this is the 3, 4, 5 triangle. Okay, the slope is 3, 4, 5. So we will be using that to break down the components of ID. Okay, so what we will be using for us to cancel the effect of CD and IJ is, I think, if we will to take summation of forces vertical, since the only unknown with vertical is your after the member ID. Okay, so to summation vertical, let's say going up positive. So what are the, so first again, when load is within your AC, so that gives us going up positive AB, and then of course the component of this, or this first is negative 1 going down, and then the component of ID is going down. So the vertical, so what is the vertical? That is 4/5. So negative 4/5 of your unknown ID. Simple algebra, you will have this as 5/5 times the AB minus 1, substitute AB. Okay, we calculated again that one. And then simple algebra, you will end up with negative x over 48. So that is good for x 0 to 30. And then moving on, when the load is within your CD, where the section is passing through. Okay, so again, that is 30 to 45. Established by, of course, we need first to calculate FC. Since again, it so happened that we are still on the same scenario as a while ago, the reaction FC is the same as what we calculated. Okay, so now we will to carry that FC. So summate vertical, this will now be included instead of that one keep. So going up AB, and then FC going down is negative, and the component ID is negative 4/5 going down, so negative. Simple algebra, again 5 over 4 of AB minus FC. Substitute AB and FC. Okay, this and that value. You will end up with x over 16 minus 5 halves, good for x 30 feet to 45. And lastly, when the load is after D already, it's already completely on the other side. So that is 45 feet to 90. And then if I have to take summation of forces vertical still, AB is going up, and the only other force to consider is the unknown ID. So component is negative 4/5. Simple algebra, that will be 5/4 of AB. Substitute AB, you will have 5/4 minus x over 48, good for x 45 feet to 90. Okay? And then lastly, we will now draw the response or the influence line of our member DI or ID. So again, as you can see, that the DI is of course the same as ID. Just like what we are doing before. That is just a matter of naming. Okay? So when DI is this 0, when the x is from 0 to 30, this is the DI, and then so on and so forth. So substitute the boundaries. Okay, so at 0, that will be 0 of course. At 30, that will be 30 over 48, or that is in decimal exactly negative 0.625. And then when that is 30, substitute to this equation, that will still give us the same negative 0.625. You can check that one, since again that should be connected. And then at 45, that will be giving us positive 0.3125. So this is the exact value. Okay. Better if there's an exact value or fraction, that is what we will be inputting on the influence line, since later on we will be using this as a value. This is not the final answer, so it is better to use the exact values. So 0.3125 positive, and then substitute 45 to the last response equation, the same. And then lastly, the 90 will give us negative 0.625. So this is the response influence line for the response of DI. Okay, that's it. That is the difference of trusses with beams and frames. In beams and frames, the movement of the load is continuous. However, in trusses, since we assume that the forces or the joints, the loads are acting at the joints, then we need to consider the movement. Okay, just like this one. When the load is within CD, we cannot just calculate that as at the distance from CD or within the CD. It should be calculated as the reaction within the joint, since again the load should apply on the joints. Okay, so that's it. That is for the influence line for trusses. So thank you very much. If you have any question, you can comment that one below the video, or we will discuss on the live meeting. So thank you very much for watching.